air standard Otto cycle. In the today lecture, we're going to discuss the analysis of air standard Otto cycle. In this, we're going to derive the expression for efficiency and the work done. Okay. See, this is a PV diagram, pressure versus volume diagram for this. See, this consists of this is the PV diagram and TS diagram. It consists of following four process: process 1 to 2, the reversible adiabatic compression; process 2 to 3, heat addition at constant volume; process 3 to 4, that is reversible adiabatic compression, that is expansion; and process 4 to 1, heat rejection at constant volume. This process is also called as a constant volume cycle because the heat is added at partially at constant volume and partially totally at constant volume, and heat rejection takes place at constant volume also. This process 1 to 2 is called as compression. The compression should be the adiabatic, reversible and adiabatic compression of the air is taking place inside the compression, that is cylinder. And 2 to 3 is heat addition. The heat addition is said to be the constant volume heat addition, constant volume heat addition. Hence, here V2 is equals to V3. And process 3 to 4 is called as adiabatic expansion, reversible adiabatic expansion of the gases. And 4 to 1 is heat rejection. This heat addition and heat rejection both taking place at constant volume, so this process is also called as constant volume cycle. Okay, this is a TS diagram. This is a volume V equals to C and volume V is equals to C. If you draw these three lines, from this 1 to 2 is called as, this is called as a compression, and 2 to 3 is called, this is a heat addition of the heat, that is heat supply at a constant volume, and here this is called as a heat rejection, the heat rejection at a constant volume. Okay. This cycle consists of this following process. It consists of four processes, and these are shown on this PV and TS diagram. Okay. Next, this is a cycle analysis of an Otto cycle. That is, this is constant volume. For 1 kg of the air, heat supplied is equals to, the Qs is equals to Cv into Ts minus T3 minus T2. See, this is a TS diagram. On this TS diagram, this is a T3 minus T2, that is the heat supplied is equals to Qr is equals to, this is T4 minus T1, this is a T, that is a into Cv, this is a heat rejected. Work done is the thing, but heat supplied minus heat rejected. That is, if you put the value Cv into T3 minus T2 minus Cv into T4 minus T1, then efficiency is equals to work done by heat supply, work done by heat supply, work done by heat supply. The Qs is equals minus Qr by Qs. Qs get cancelled out. Put this value here, 1 minus Cv get cancelled out. T4 minus T1 by T3 by minus T2 is equals to 1 minus T4 minus T1 divided by T3 minus T2. This is the efficiency of this equation, that is in terms of the temperature. Okay. The next slide. See, this is the next one, and in this, see, this is a efficiency in terms of temperature for process 1 to 2, that is PV equals to constant adiabatic compression process. This is a pressure versus volume diagram. This is a pressure versus volume diagram. This is, then you can write T2 is equals to T1 into V1 by V2, there V1 by V2 in raised to gamma minus 1. Then what is the compression ratio? The RC is the compression ratio, that is a V1 by V2, and if you put here the value, this is equation number A. And for process 3 to 4, this is expansion process, T3 by T4 is equals to V4 by V3 raised to gamma minus 1. And if you put here, this see the value carefully here, the V1 is equals to V4, and here the V2 is equals to V3, then the V1 is equals to V4, that is again RC raised to gamma minus 1. I put this value both in here in this equation, and you getting this equation, as T4 minus T1 as it is. Here put the value of T3 is equals to T4 into Rc raised to gamma minus 1 minus T1 into Rc raised to gamma minus 1. Then take from the denominator Rc raised to gamma minus 1 constant common, then this will be cancelled out, and the efficiency of an Otto cycle is a function of, that is, compression ratio and adiabatic index. Okay, this is the efficiency of this Otto cycle. Next, that is efficiency of Otto cycle. Calculate, say, let's see the example problem. Calculate I will say, if the compression ratio of a petrol engine is a 6, find its air standard efficiency take gamma is equals to 1.4. Then they ask, that is, Rc is equals to given is equals to 6. Then we have to calculate if that efficiency is equals to 1 minus 1 upon Rc raised to gamma minus 1. This equals to 1 minus 1 upon 6 raised to 1.4. Calculate this will be the efficiency into 100 in percentage dash dash percentage.